Welcome to Math 361, Statistical Methods 1. This is the Week 2 online lecture video covering an introduction to probability. Our outline is to cover an introduction to probability. Now, before we start talking about how to assign probabilities, we have to build up the correct mathematical model for what's known as a random experiment. Our probability theory will be based off of this idea. So a random experiment is pretty simple. It's any process, real or imagined, whose outcome cannot be predicted with certainty before the experiment is run. Some common examples that we'll use quite often in this course include flipping a coin, rolling a die, drawing a card. Those are always easy ones to fall back to because we have some life experience with those random experiments, but also something more complex like selecting a simple random sample of size n. Right? And that's what we're going to need to do when we return to the science of statistics and doing statistical inference. We'll be selecting random samples, so being able to come up with a mathematical model here for that random experiment means we'll be able to talk about variability and uncertainty mathematically at that point. So every random experiment has three key components that need to be modeled mathematically. If you think about the example of rolling a die, first we might be interested in what is possible. So if it's a six-sided die, we would say, well, I could get a 1, a 2, a 3, a 4, a 5, or a 6. In our mathematical model of a random experiment, what is possible will be answered with a sample space. We'll explain that more in upcoming slides. After you know what's possible, numbers 1 through 6, what are we interested in observing? It might be something simple like, am I going to get a 2 or maybe a 5? Or something more interesting, maybe am I going to get an odd number, a prime number? Right? Multiple outcomes may correspond to observing an even number, 2, 4, or 6. So in our model, those will be events, or mathematical events, we sometimes say. Finally, after we know what's possible and what we're interested in observing, we'd like to know how probable it is we make a given observation. This is where probability theory comes into play. We'll define a probability function or a distribution later on. That's where the probabilities come into the problem. So to explain some of these concepts a little better, let's look at a nice little cartoon here of rolling a six-sided die. So on the left, we have the real-world, empirical, random experiment. There are 6 physical outcomes of rolling this six-sided die. On the right-hand side is my picture of my mathematical model. So what we need here is set theory from mathematics. And if you haven't seen that in a while, there is an optional video for week 2 that you can watch in order to brush up on set theory. So in this case, this lima bean shaped drawing is just my picture of my set, my visualization. And in it, I have some points, 1 through 6. So in the upper right-hand corner, you see capital S is equal, then in the curly braces, 1, 2, 3, etc. there. That is my sample space. It defines everything or all possible outcomes of my real-world random experiment. And note here in blue, I have mappings essentially associating each real-world outcome, say getting a 2 on a die, with an element in the sample space. And these elements we'll call sample points. In the drawing here, this is how we usually set it up, where we have a one-to-one mapping. Every outcome in the real world has a sample point corresponding to it, and every sample point has one outcome in the real world corresponding to it. It doesn't need to be that way. In essence, if there's a possible physical outcome of the experiment, then we'd like to have that mapped to exactly one sample point. And then every sample point has to have at least one real world outcome corresponding to it. So we don't want to have as like an extra sample point maybe labeled 10 with no outcome of the experiment corresponding to that, right? We don't want extraneous sample points here. So that's kind of the idea. That's how I'm going to have to build up my, how do I get a physical real world process into a math problem? Well, we're going to use set theory here, our sample space with our sample points. Now, moving on to the second key ingredient, that is, what would we like to observe? So if we're interested in observing something simple, like just getting a 2 on a die, I can look at a subset of the sample space. That's labeled A in this picture, and it's a set containing just the sample point 2. So that is a subset of the sample space, meaning it is contained within the larger sample space. That's known as a simple event. It's an event because an event is defined to be any subset of a sample space, and it's simple because it contains a single sample point. Compare that to the event B in blue, which corresponds to getting a 4, 5, or a 6 on the die. So that would be getting 4 or more on our roll. So B contains the sample points 4, 5, and 6 in the lower right-hand corner there. And we refer to that as a compound event. It's made up of several simple events combined together. Now, in addition to simple and compound events, there's also the certain event. That is the sample space itself, 1, 2, 3, 4, 5, 6. That always occurs. And then there's also the impossible event in the lower left-hand corner. That's the circle with a slash through it, or it's also labeled as empty braces. That's the impossible event. That has no sample points in it. It's impossible because something has to occur on our run of the random experiment. And I should note here that when we actually go and run the random experiment, an event is observed if one of the sample points in that event corresponds to the physical outcome of the random experiment. So if I go and roll the die and get a 5, event A was not observed, but event B was. If I roll a 6, same thing. A is not observed, but B is. And in that case, the event S, the whole sample space, the certain event, always occurs. That's why it's called the certain event there. So a lot of terminology here, right? Just know that when we're modeling a random experiment, we use set theory. And then we have the sample spaces and events. In the end, we're going to want to assign probabilities to these events. So a little vocabulary summary here. Sample space is a set of elements called sample points. An event is any subset of a sample space. Simple events contain only a single sample point. Certain event, which is the sample space, contains all sample points. The impossible event contains no sample points. I didn't mention this in the previous slides, but any two events are said to be mutually exclusive, or sometimes we use the phrase disjoint, if they cannot occur simultaneously. In other words, A intersect B, which we sometimes read as A and B, that set is equal to the empty set. So for an example on that previous slide, events A and B are mutually exclusive because on a single run of the random experiment, a single roll of the die, I cannot both end up with a 2 and a number 4 or larger. Right? Those are mutually exclusive. Their overlap, if I want to think about it that way, is none. There's no points that are in both of those events. Note that all simple events are mutually exclusive, right? Because each one contains only a single sample point. Finally, the complement of event A, denoted by A with a bar over it, is a set of all sample points not in event A. All right, so this would be a good time to pause and make some flashcards to start getting the language down of probability. We'll be using these terms throughout this week's lecture and next week's lecture and several lectures after that. So what about probabilities? That would be the third component of our mathematical model of a random experiment. Well, the thing about probability is consider the random experiment of flipping a fair coin. What do we mean by fair? Now there's several answers or possible answers to this question depending upon a person's background. Some common ones I've gotten in the past from students are you're just as likely or probable to get heads as you are tails. The chance of getting heads on a coin flip is 50%. Other students have said about half of the tosses will land showing heads. Finally, a few students will say you will get about the same number of heads and tails. Well, if we think about these statements a little bit more, it turns out those first two statements, you're just as likely or probable to get heads or tails, or the chance of getting heads is 50%, that's based on our intuitive understanding of probability theory. That's really using the results of what we're about to talk about. Our theory we're going to build up will result in these answers in red being true. Now, the third option, about half the tosses will land showing heads, we'll look at that in a moment here and see that that also is correct. This is known as the relative frequency approach of for probability theory. Finally, the last answer, you will get about the same number of heads and tails. That seems very similar to the answer in blue. You get about half of the tosses, but the answer in blue is talking about proportion, whereas the answer in black is talking about frequency, counts. So we'll take a look in Excel to see what really happens. What's the difference between talking about relative frequency or proportions and counts or just regular frequencies. So here we are in Excel. What I'm going to look at here is simulating flipping a coin, a fair coin, many times, thousands of times. So what I've done here is created a random number, 0 or 1. 0 will correspond to heads, 1 will correspond to tails. So I get a 0 in the first coin flip. I label that an H. And now what I calculate is a running relative frequency of the coin landing on heads. So after one coin toss, I got heads, so I've gotten 1 out of 1 so far. After the second coin toss, I've now gotten 1 heads out of 2, so the relative frequency now is 0.5. After 3 coin tosses, I've gotten 1 heads out of 3, so now the relative frequency is 1/3. Out of 4, I now got 2 heads out of 4, so now it's back to 0.5. So every time I flip the coin again, I calculate a new relative frequency of the coin landing on heads. And finally, which we'll look at in a little bit, I also here have calculated the difference in numbers of heads and tails. So as I go along here, well, now I've got 1 head and no tails, so 1 minus 0 is 1. Now I've got 1 of each, so the difference is 0. Now I got 2 tails and 1 heads, so now heads minus tails is -1. So that's what this last column is. So first, let's look at visualizing the relative frequency of the coin landing on heads. So here on the vertical axis, I have the relative frequency, and on the horizontal axis, I have number of coin tosses. So I go up to about 970 coin tosses. So note here that the relative frequency bounces around a bunch, but it starts to approach something close to 0.5. It's still around 0.51, 0.52 or so far there. It's not exactly 0.5 like I would expect for a fair coin, but it's close. Now what I want to do, the wonder of computers here, is I'm going to re-flip the coin 970 times and see how my results change. All right, the graph looks different, but note that the relative frequency still bounces around, but then starts to hover and approach near. Now it's a little below 0.5, 0.49, but it's nearby. Right? It's still, look at that, the end of 0.981, so it's coin toss 981, I'm at 0.5005. So let's go and re-flip the coin 900 so times more. Once again, it bounces around for a while. It's hovering a little below 0.5, but it's still getting closer to 0.5 after about 900 coin tosses. Do it again, it's close to 0.5. Again, close to 0.5, starting a little above though. Again, approaching 0.5. So every time here, you see there's some consistency. My relative frequency, as I do more and more coin tosses, it seems to be approaching 0.5. So Why is this occurring? What am I seeing here? This is known as the law of large numbers. When I have a random experiment that is repeatable and each repetition is independent of the previous results, I see that the long run relative frequency of an event occurring, like getting heads here, seems to approach some fixed value. And that might be a number I would investigate for assigning a probability. Still showing up around 0.5. So once again, that law of large numbers we just saw illustrated in Excel says that as the number of independent trials increases, the long-run relative frequency of an event being observed approaches a single value. This gives us a good starting point for talking about what number should we assign as a probability. If this relative frequency approaches a single value, that single value is a good candidate for the probability of that event occurring. Now, there is an unfortunate downside to this, that if we build our probability theory off of this relative frequency approach, it requires us to have the ability to perform a series of independent trials, right? Repeatable independent trials. And that's a big ask. All right, so that's kind of the downside of the law of large numbers. Now, let's quickly look at the difference between talking about relative frequency, which the law of large numbers applies to, saying that the proportion of heads approaches 0.5. And let's compare that to looking at counts in general. Does the number of heads approximately equal the number of tails as we flip the coin more and more and more? So returning to Excel, now we're going to look at what happens at the difference in numbers of heads and tails. Is saying that you get approximately 50% tails the same thing as saying you get approximately the same number of heads and tails? Let's compare relative frequency to frequency itself. So now we looked previously at the relative frequency chart. Now we're going to look at the difference chart. And once again, I'm going to reflip the coin 980 times. Note here on this first one that I don't see the difference in heads and tails. This is number of heads minus number of tails. I don't see it really approaching any number like we saw in the relative frequency chart here. So let's go back and flip these coins some more. Still not really approaching anything. It's down in the negative 25 or so. It's up around positive 30. That's down around negative 70. So in this case, even though if I go to relative frequency chart, the relative frequency, go back. The relative frequency is approaching 0.5 still. It's at like 0.46 here. The difference chart seems to be going further and further negative. That means I have more tails than heads. More coin tosses. There doesn't seem to be any discernible pattern. It goes up, it goes down, it bounces back and forth. I don't see that nice approach going on. So the law of large numbers here does not apply to frequencies themselves, but only to relative frequencies. In fact, you can show that if I could do this infinitely many times, the probability of me getting the same number of heads and tails in coin flips is 0. It's just not going to happen, even though the relative frequency will still approach 0.5. One final example of why the law of large, or to see how the law of large numbers applies to proportions and not counts. Here is a made-up random experiment of continually flipping a fair coin. Each row corresponds to a different number of tosses, starting at 10 and going up to 100,000. And I want to note here that as the number of tosses increase, Now I've made up these numbers, so this didn't happen from an actual toss, but it's a possible result of this experiment. I see in the rightmost column that the proportion of heads starts off around 60%, but will approach 0.5, what we saw with the law of large numbers. But the difference between the number of heads and number of tails, as that proportion approaches 0.5, I can make the difference increase without bound. So it's getting larger and larger and larger. It never approaches a specific value. So this limiting behavior, as you might say, appears to hold for proportions, but not for frequencies themselves. All right, so let's return to the problem of assigning probabilities. So far, we've seen that there is this relative frequency approach. If we can repeat the random experiment many times independently each time, we might be able to show that the relative frequency approaches a single value. That would be a good value to assign as the probability of an event. But there's also two other ways that are usually discussed. One is the axiomatic approach. That's what we will use in this class. And the third is the personal or subjective approach. The personal or subjective, that's more akin to you going to school and then thinking, oh, maybe I didn't turn off the stovetop. What's the probability of that happening? Well, you're kind of forgetful. You've done it before. Maybe you say there's a 10% chance that you left the stove on. Well, that's not based off of repeated independent trials. That's kind of your own guess at a probability based off of personal experience. I said we'll be focusing on the axiomatic approach. This axioms are rules-based. We're going to come up with a few rules that probabilities have to follow. And what we'd like to happen out of this is that when we define these rules, that they are consistent with results from the relative frequency approach. Meaning, for tossing or flipping a fair coin, the law of large numbers says that the relative frequency of getting heads approaches 0.5. We'd like our axiomatic approach then to assign the probability of getting heads to be 0.5. We'd like those two to match up. So the three basic rules of probability are as follows. One is for all events, we assign a non-negative number for probabilities. So they're greater than or equal to 0. Rule number 2 is that the probability of the certain event, S, the whole sample space, is equal to 1. Now those first two taken together also kind of will lead to a later rule that says that probabilities not only have to be greater than or equal to 0, but the probability of any event also has to be less than or equal to 1. So, it's kind of arbitrary, but we kind of stick to the 0 to 1 range for probabilities. If we report a probability as a percentage, then it becomes between 0% and 100%. But no one should ever be reporting a probability of 2.4 or anything like that. The third and final rule will be one of our more useful computational tools, and that is for any two mutually exclusive events, A and B, the probability of A or B, or in set notation, that would be the probability of A union B, is equal to the probability of A plus the probability of B. So when I want to know what's the likelihood that one event or another occurs, if you can insert that word or into it, then I know that if they're mutually exclusive, right, that has to hold. Right? If I don't know that, I can't use this formula. But if they're mutually exclusive, then I simply add the probabilities together. So quite often, probabilities of unions, students associate that with addition. Any probabilities we assign that satisfy these three rules are considered acceptable. All right, so we'll say find some acceptable assignments of probabilities. That means we want to assign probabilities consistent with our rules. So for example here, suppose you flip a coin. Find an acceptable probability assignment for all outcomes of the random experiment. So whenever I'm assigning probabilities, even if I don't explicitly state it, I should always be thinking in the back of my mind, what is the sample space? Then what are the events, the possible observations I want to make? And only after I've thought about that do I start to assign probabilities. So in this case, I'm flipping a coin. My sample space consists of only two possible outcomes, getting heads or getting tails. And therefore, I have two simple events I can think of. Event H, which would correspond to getting heads, and event T corresponding to getting tails. Now, since the sample space is really the union of these two simple events, and I know that the probability of the entire sample space has to be equal to 1, I can conclude that I could take the probability of getting heads and assign that any number between 0 and 1, and then the probability of getting tails would have to be 1 minus that number. So I could set k equal to 0.2, and that would say the probability of heads is 20%, the probability of tails is 80%. I could say the probability of heads is 47%, then the probability of tails is 53%. There's infinitely many acceptable assignments in this scenario. Now, k equals 0.5 will make the most sense because it's consistent with the law of large numbers. So that might be acceptable and reasonable, right? K equals 0.5 seems like a reasonable assignment, but it's not the only choice according to my mathematical theory, right? I'm just building some rules, and my probabilities have to satisfy those rules. So 3 more rules of probability. I mentioned this earlier a couple slides ago, but for all events, not only do probabilities have to be greater than or equal to 0, they also have to be less than or equal to 1. Rule 5, the probability of the impossible event, that's the empty set, that's equal to 0. Now finally, the probability of the complement of any event is 1 minus the probability of that event. So if I go back to the previous slide, the probability of heads was k. Well, what's the complement of event H? That'd be all the sample points not in H. Well, that's just T. So according to rule 6 here, the probability of getting tails has to be 1 minus the probability of getting heads. And that's precisely what I had on the previous slide there. So it turns out that these 3 additional rules of probability could all be derived from the first 3 rules of probability. So we're just stating them here just to have them written down, and so we remember these are the kind of boundaries within which our probability assignments must work. So if we have infinitely many possible acceptable assignments of probability, like with that coin toss problem, how do we come down to, or how do we find the reasonable assignments? Well, we make assumptions now. We take these rules of probability and we add to them assumptions. The most common assumption we add is that all outcomes of a random experiment are equally likely. When we make that assumption, then the probability of an event A occurring is given by this formula. Now, this is a formula everyone should have down. The probability of event A is equal to, now in the numerator it says n of A. Well, that's just shorthand for the number of outcomes or sample points corresponding to event A being observed. And in the denominator, ns, that's the total number of possible outcomes or sample points. In other words, when I assume equally likely outcomes, assigning probabilities comes down to counting sample points, counting the sample points in that event, counting the total number of sample points in the entire sample space. Now, under this assumption, you say, well, why is this the formula when you work under this assumption? Well, once we make the assumption of equally likely outcomes, this is the only formula that works. We have to assign probabilities this way. This is also referred to as the classical approach to probability. So the next slide, I'll prepare you, has a lot of math on it, but I just want to go through and derive this formula here. Why must this be how we assign probabilities when we assume each outcome is equally likely? So in the upper left, I have an example sample space. There's sample points S1, S2, S3, S4. Those are in event A. And there's a ... going up to Sn. So there's n sample points in the sample space. And I'm going to use rules 2 and 3 with rule 1 kind of in the background there. So the idea here is as follows. I start with the probability of the sample space. Well, that's the probability of the set that contains all sample points. Well, I can take any event like that, the certain event, and instead write that as a union of simple events. So now I have the probability of set S1 union the set S2. So those are all simple events. But what I have now is a probability of a union of mutually exclusive events. All simple events are mutually exclusive. So rule 3 says that to calculate that probability, I can add up the probabilities of the individual simple events here. So the next line says the probability of S1 plus the probability of Sn. And here's where my assumption comes into play. At this point, I've said each outcome is equally likely. So I don't know what number to assign to that, but I know it's going to be the same number. So I use lowercase p to represent that. And since I have n simple events here, whose probabilities I'm adding together, that's p plus p plus p n times. Well, the shortcut to repeated addition is multiplication, so the whole thing adds up to n times p. So in total now, I've got the probability of the certain event s is equal to n times p. Well, rule 2 says that the probability of the certain event is equal to 1. So I get n times p equals 1, or that unknown probability p is 1 over n. So when all outcomes are equally likely, each simple event should be assigned a probability of 1 over n, where n is the total number of sample points or possible outcomes. It then follows that the probability of event A in blue will once again do the same argument. Well, that's the probability of the event containing S1 through S4. I take that compound event and break it up into a union of simple events that are mutually exclusive. Then I can break up that probability of a union into a sum of probabilities of simple events. And in this case now, I know that each one of them has a probability of 1 over n. That's what we just proved above in red. So I have 1 over n plus 1 over n plus 1 over n plus 1 over n. Well, that's repeated addition again. Turn it into multiplication. I get 4 over n. That n in the denominator is the total number of sample points, and that 4 in the numerator is the number of sample points corresponding to my event A in the picture. So that's where this formula on the previous slide comes from. The rules plus the assumption result in this formula. Now, what we've got to be careful, though, is that we make sure the assumption of equally likely outcomes is reasonable for a given problem before we invoke this formula. So let's look at an example. Suppose you roll a 6-sided die twice now. What is the probability you roll the same number both times? So to approach this problem, think in the back of mind first about, well, what is the sample space? What am I interested in observing? And I want to introduce the idea here of a tree diagram in the lower left-hand corner, where I kind of have the first roll, and I look at branches for each possible outcome of roll 1. That would be 1, 2, 3, 4, 5, 6. And then at the end of each of those branches, I've gotten some number on roll 1, and then I'm going to visualize roll 2 by another set of branches. So I only drew one set of 6 branches for roll 2, emanating from getting a 3 on roll 1, but each one of those branches from roll 1 would have another set of 6 branches coming out of it in roll 2. It's just very hard to visualize. And the idea here is if I use this tree diagram to kind of visualize what's going on in this experiment, then if I start at the beginning of the tree and travel along a path, in red here you see that I've got a 3 and then a 2, that gives me one outcome of a random experiment, the ordered pair 3, 2. So the idea is if I can set up a tree diagram like this, I could easily then list off all the possible outcomes for this multi-stage random experiment. All right, it's like I'm doing one random experiment, rolling a die, and then doing it again. So it's multiple stages. Now, it turns out in this case, I don't really care. I mean, I can do that. I could write out all possible outcomes of the random experiment, but I don't really care about that because I'm rolling a die twice. And in that case, I'm assuming every possible outcome is equally likely. So the event that I'm rolling the same number both times, I want to find the probability of event A. Because each outcome is equally likely, what I really only need to do is count the number of outcomes corresponding to event A occurring, and then also count the total number of possible outcomes. Now in the numerator, NA, well, I have to think about the same number both times. Well, I can just think about that one. I can get a 1 both times, a 2, a 3, a 4, a 5, or a 6. So there's 6 different possible outcomes where I get a repeated number. So my numerator is going to be 6. Now what about my denominator? Well, if I use the tree diagram, I could list out every possible outcome and then just count them, 1, 2, 3, 4, etc. there. Instead, I want to look at a shortcut down here in purple. Right? This is because I'm only interested in the number now of sample points, not listing out every sample point. So I see that in roll 1, in the first stage of this experiment, there's 6 possible outcomes. In roll 2, there's 6 possible outcomes. So if I want to count the total number of possible outcomes for 2 rolls, I can break down this larger counting problem into smaller counting problems. Count what's possible in roll 1, count what's possible in roll 2, and then multiply them together. So I get 6 times 6, or 36 total outcomes. This is known as the fundamental counting rule. We'll use it quite often. If I were to list out all outcomes of the experiment, I'll see that there would be 36 possibilities, starting with 1, 1 and going all the way up to 6, 6. So I have 6 for my numerator, 36 as my denominator. Divide that out, I get 1/6 as the probability I would assign to the event of getting both, or getting the same number both times. That is the classical approach to probability. Now that fundamental counting rule I mentioned states that the number of ways that 2 events can occur, given that the first event can occur m ways and the second event can occur n ways, is m times n. Right? So we break down a big counting problem into smaller pieces and then multiply all the ways those pieces can happen together. A common everyday example would be if you had in your closet 3 shirts, 4 pants, and 2 pairs of shoes, and you want to know how many different ways could you pick a pair of pants, a shirt, and some shoes. You would just multiply the 3 shirts times the 4 pants times the 2 shoes and have 24 different possible outfit combinations. That is what the fundamental counting rule states. So before we finish up this video, just look at one more example applying the fundamental counting rule along with the classical approach to probability, where we assume all outcomes are equally likely. Suppose you have a standard deck of 52 playing cards. Is it more probable to draw 2 face cards in a row if you draw with or without replacement? So what we really need to do here is find 2 different probabilities and see which one is lower or higher. First, we'll look at drawing 2 cards in a row if we draw with replacement. So let's say I'm going to pick a card out of my deck and then put it back, and now I'm going to pick another card after some shuffling. So we'll call this event A, getting 2 face cards in a row. So since I'm randomly drawing and I'm mixing in between there, all possible outcomes are equally likely. So to find the probability of A, I'm not going to actually go find the sample space. I could. Sample space consists of ordered pairs like Jack of Hearts, Queen of Clubs, 2 of Hearts, 4 diamonds, things like that. But I'm only interested in counting how many outcomes correspond to getting 2 face cards in a row and how many possible outcomes are there in total. So usually it's easier to start trying to find a denominator. So how many different ways can this random experiment end? Well, for pick number 1, I have 52 possibilities. Now I pick one of them, but then I put it back in. So for my second pick, there's 52 possibilities. So in total, there's 2,704 different ways to pick 2 cards, as long as I'm putting the first card back. So that's my denominator, 2,704. Now to find my numerator, I have to figure out, of those 2,704 possibilities, how many of them result in getting 2 face cards in a row. Well, I look at this pick by pick. For pick 1, there are 12 face cards, the 4 jacks, the 4 queens, and the 4 kings. All right, if I pick one of them, it doesn't matter. I put it back for pick 2. So for pick 2, there's going to be 12 face cards again in the deck. So how many outcomes correspond to getting 2 face cards in a row? Well, 12 times 12 or 144. So that's going to be my numerator. So in the end, my probability of getting 2 face cards in a row with replacement is 144 over 2,704, or approximately 5%. Now let's compare that with doing the same random experiment, but not replacing the cards. So we'll call this event B when we do this without replacement. Now, even though I'm still drawing 2 cards, because I've changed the structure of the random experiment, my sample space would be different. So to find the probability of event B occurring, I'm going to have to once again find how many different possible outcomes there are and how many different outcomes correspond to getting 2 face cards in a row. So looking at the denominator first, n of s, I see that for pick 1, there's 52 possibilities. However, I'm not putting that card back for pick 2. So now for pick 2, there's 51 ways, or 51 possible choices. So in total, there's 52 times 51, or only 2,652 possibilities for this scenario. So my denominator has decreased. Now I look for the numerator, and a b, how many different ways can I end up with 2 face cards in a row? Well, for pick 1, there's still 12 face cards, the jacks, the queens, the kings. But now let's assume I pick one of those. Now there's no longer 12 remaining, there's only 11 left for pick 2. So the total number of ways I can get 2 face cards in a row is now just 12 times 11, or 121. So my numerator is decreased as well. When I plug those 2 numbers in and calculate the probability, I get about 4.5% now. Remember, in the previous slide, it was a little more than 5%. So I see that with replacement, the likelihood of getting 2 face cards in a row is slightly higher than if I don't replace the card after the first draw. Now the cool thing here is if you think about the long approach, and that would be directly listing out all 2,652 possible outcomes of the random experiment, explicitly defining the sample space. If I imagine the tree, the first stage would have 52 branches, 1 branch for each possible card. Now let's say I take the branch corresponding to get an ace of spades. So for the second stage of the experiment, there'd be 51 branches coming off of the ace of spades branch. Right? It would include every card except the ace of spades because that one's already been picked and I'm not replacing it. Now, if instead I followed the branch for the 2 of clubs, in the second stage, there would be 51 branches coming off of it. It just wouldn't include the 2 of clubs because it's already been selected. So this is a case where the branches in the second stage are actually dependent on what happens in the first stage. There's different cards available for pick 2 depending upon what you picked in pick 1. However, what's important for us is that regardless of what you pick for the first card, for the second pick, there will always be 51 cards remaining. So in that scenario, the fundamental counting rule can apply. Now, how could I break this? Well, I could change the game that we're going to draw these cards without replacement unless you pick a heart first. Then we replace it. Well, in that scenario now, in the second stage, you're going to have a different number of branches depending upon which path you went in the first stage. If I got one of the cards that made me do replacement, then I would travel that path and I would have 52 possibilities in the second stage of the experiment. But if I got, say, a club on the first draw, I would still only have 51 because I wouldn't be replacing the card then. So once I mess with the random experiment in a way such that there's not the same number of possibilities in a later stage because of something that happened in an earlier stage, then the fundamental counting rule does not work. However, I don't think we'll really encounter that too much in this course. Most of the time, we will be able to apply this fundamental counting rule. It is the first counting rule we encounter. There are more complex, advanced counting techniques we'll talk about in class on week 3. So to summarize here, we have this notion of a random experiment, which you want to model mathematically. You want to know what's possible, what are we interested in observing, and how likely it is we are to make a given observation. So we need a sample space, events, and a probability assignment, which we'll call a probability function or a distribution later on. Acceptable assignments of probabilities obey a set of probability rules. In a good scenario, if the random experiment is repeatable, our acceptable assignment will agree with the law of large numbers result, like we saw in Excel. When we further assume that all outcomes are equally likely to occur, then we have a formula for assigning the probability to an event. We have to just count how many ways can the event we're interested in observing occur. That's the numerator. And then how many possible outcomes are there in total? That'll be the denominator. This is also known as the classical approach to probability. Finally, because now when all outcomes are assumed to be equally likely, we have to count sample points. We come across needing some counting rules or counting techniques. And the first one is the fundamental counting rule that states if we can take a large counting problem, especially for like a multi-stage random experiment, break it down into smaller pieces, figure out how many ways each of those smaller pieces can occur, then what we want is to just multiply all those results together to count how many ways the entire multi-stage process can occur. Right? We'll be using that quite a bit in class this week.